Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today is the final talk of my intern, Simon Telvold from Switzerland, from ETH and FHNW. So with Simon we have started a project about the hash function SHA-1, a former and in some systems still current standard of hashing, which is still quite fast. And despite collision attacks which appeared in 2005, we are still unable to produce practical collisions, and that's why the security of SHA-1 is now evaluated in different ways. For example, preimage attacks, which in some systems are more vulnerable and pose a bigger danger, are now under attention. And with Simon, we have tried to investigate the preimage resistance of first reduced round SHA-1, but eventually we have something to say about how difficult it is to find the preimage for the full SHA-1. Well, the thing is that results on full version of compression function and block ciphers is not a trend, because well, before all this decade, the most cryptanalytic results are on reduced round versions of, say, AES and SHA-1, SHA-2. And now I hope we continue a very recent tendency to present some meaningful results on the full version of a hash function. In this case, SHA-1, but with Simon we also have some interesting results on SHA-2. And how resistant SHA-1 is against preimage attacks, Simon will say now.
Thank you very much for this introduction. I could skip now my first few slides, but I will not do so. Yes, thank you for coming to this talk. And let me just start with some hash function basics. I know that you know what is a hash function, but just for warm-up, it takes as input an arbitrarily long message and produces an output of fixed length. Typically, the length of this output is quite short. So for SHA-1, for example, it's just 160 bits. And yes, these kind of functions are used everywhere in cryptographic protocols. Most of you probably know more applications than me of hash functions. It's everywhere, omnipresent in cryptography. And in an ideal world, it is expected that such a function behaves like a random oracle. But in the real world, we all know that it's not possible to build a random oracle. And so what we do, or what we will do in this talk, we just go back to a bit more traditional security requirements, which are these three properties: collision resistance, preimage resistance, and second preimage resistance. And in this talk, specifically, we focus on preimage resistance. Preimage resistance is the following. We have given one output, so one 60-bit string for SHA-1, and what we want to find is an input of arbitrary length that maps to this output. This input is typically called a message, and is the preimage of H. And the hash function is considered preimage resistance if finding such a collision is hard. So meaning the best strategy we can apply to find such a preimage is just trying several messages until we have found a suitable one. So this is not exactly exhaustive search, because we cannot exhaust the whole input space, but we call it exhaustive search because it's just random trying messages. And for this, we would have to try in average 2 to the n messages until we find one that works. And the computational cost of this would be 2 to the n computations of the hash functions. And when we can do it faster, when we find a method that can do it faster, we found something interesting. And in this talk, we will show two strategies to do it a bit faster. One that works for the full number of rounds of SHA-1. So what do we know about SHA-1? Dmitry already summarized it very briefly. SHA-1 was designed in 95 by NSA, and then in 05, at crypto 05, collision resistance was broken. Broken means really there is a strategy that can find collisions in almost practical time. No collision was found so far, practical collision, but Christian almost found one. But SHA-1 is a broken hash function. But what we analyze now is just preimage resistance of this hash function. And what's known about preimage resistance, the results are from crypto 08 and crypto 09. The first result presented by Christian and his colleague, Christophe de Cagnières, was for 44 steps, and the full SHA-1 has 80 steps. Maybe you should know this. And they could give a technique that allowed finding a preimage in a complexity, so essentially after 2 to the 157 trials. 1 year later, Aoki and Sasaki gave a technique that worked a little bit faster than exhaustive search for 48 steps. And what we can do now in this paper is we will say something on the full number of hash functions, on the full number of steps, which is these 80 steps. And it has essentially the same complexity as the result from crypto 09, which only worked for these 48 steps. But it is very close to exhaustive search. We don't really consider it as an attack on the hash function, but just you will see it. We will call it accelerated search to say that it is an algorithmical improvement over the naive exhaustive search. But for reduced variance, we show a technique that allows us to compute preimages significantly faster than it was done with these two techniques. So for the next 20 minutes, what I will do is first explain the general idea of preimage meet-in-the-middle attacks. Then specifically look at this meet-in-the-middle technique for when we have a hash function with linear message expansion. This is the case for SHA-1. And then I will explain the two techniques coming out of this, which allows us to do our results. This accelerated search that works for the full number of steps, and then the technique we call probabilistic partial matching, which gives these speed-ups for reduced number of steps. And for explaining the general principle of meet-in-the-middle preimage attacks, you need to know how these hash functions, so essentially all of today's hash functions, so MD5, SHA-1, SHA-2 are built. And they all are built using this Merkle-Damgard construction. Essentially, this is the construction that allows you to treat arbitrarily long messages. What are you doing? You take your message M, you append some bits of padding, and then you cut this message into several blocks. For SHA-1, these blocks have a length of 512 bits. And then you process this message block by block. You start with an initial value, and you mix it up with the first message block using this kind of function. This is called compression function. The output of this compression function you mix up with the second message block using the same compression function. And you process it like this, and the last output, this is your hash value. What we will do in this talk, we will only focus on this part here. So we will consider computing a one-block preimage of SHA-1. This is also what we have in mind when we talk about the complexity of exhaustive search, because we will measure the complexity of our techniques in terms of number of computations of this compression function, because this is the most costly part of the whole process. And when we talk about the complexity of 2 to the n, we mean, so exhaustive search with complexity 2 to the n, we mean that the exhaustive search has a complexity of 2 to the n evaluation of compression function, meaning that we are searching for one-block preimages. So we are looking now at this process here. It works like this. The message block is expanded in some way to a sequence of message words. For SHA-1, this sequence has the length 80. So we produce 80 message words, and each message word is used in one step. So we proceed then in 80 steps, starting from the IV for the first application of the compression function, and then we apply these step functions. Every step function depending on one message word. And what we get at the end is a value h prime, and the output, so meaning now what comes out here, is not this h prime, but is h prime plus the initial value. This is called feed forward and makes that it's hard to compute backwards, or not so easy. What is important here, what we will use for our attacks, is that all these step functions are invertible. So if we know h prime, we can, and we know this expanded message word, we can compute in this direction. This is what we will use essentially in our attacks. And the problem now is,
how do you go from M1 to W0 to W1?
yeah, this is, I said, in some, you expand the message in some way. In SHA-1, I will explain it later for SHA-1 more explicitly, but this can be done for MD5. It's a permutation of, so you write this as 16 message word, and then for MD5 it's just a permutation. For SHA-1 it's a linear expansion, and for SHA-2 it's something non-linear, a bit more complicated. But so for now we are not interested in this, but it's important later.
Okay,
Yeah.
one more question. So
Yeah.
if you get this one block preimage, then that automatically gives you preimage for all, like how many more blocks you want to? Is that true?
No,
Or could you just go back? Yeah. So this one block preimage, does that imply a preimage even for larger messages?
I mean, what your problem is you get some h,
Yeah.
and you just want to find some message, some preimage of arbitrary length. And we just focus on finding one block preimages, which must exist with high probability, because your input is 512 bits and your output is only 160. Of course, there are several techniques to, that force you to compute two-block preimages or even longer preimages. In most cases, it's only an advantage to compute. So the challenge is bigger when you compute short preimages in general, because there are generic techniques to compute longer preimages. Yes, and in fact, when we compute a one-block preimage, then of course this preimage would contain a padding. So some part of the preimage cannot be chosen by us, but would be fixed by the length, essentially, of this block. But in this talk, we ignore it. In the paper, we describe a very nice technique that can circumvent this, so it's not really a problem for our attacks. But in the talk, this is technicality that we avoid. So let me explain the general principle of a meet-in-the-middle technique. And you probably know it. It's a very old idea that essentially was maybe first time applied by Diffie and Hellman when they showed that double encryption with DES, with two different keys, gives you not a security of 112 bits, which would be the length of the two keys, but only the security of 57 bits. This is a very old idea that we use here. That was already used for hash functions. We are not the first using this. And so for explaining just the idea, assume that the expanded message, which I note here is this bold W. So this is this here. This expanded message can be separated into a left part and to a right part, and both parts can be chosen independently. This does not exist in a real hash function. It's just a toy example for us to think. What would I do here? I would choose several left parts and compute it starting from the IV to the middle. And I would choose several right parts and computing backwards from the, this is the H prime. So this is the target value minus the IV, so giving the H prime, the last value that we compute here. Compute them in the backward direction onto the middle. So I end up with two lists of values, and I look just for a match between these two lists. And when I have a match, so for example, when the value I receive from this computation matches with the value I receive from this computation, then I would have a preimage consisting of left part L1 and right part R0. And what it gives us, if we compute 2 to the d values in the forward direction and 2 to the d values in the backward direction, then we can in total test 2 to the 2d messages by combining every combination we can in the middle. But it only costs us 2 to the d plus 2 to the d half computations. So in total, 2 to the d full computations of the compression function. This is the rough idea, which gives us this speed up. Of course, it's a trade-off between computational cost and cost of memory, because we have to save these lists in the middle. This is the usual trade-off. But in the applications of hash functions, these lists here in the middle will typically not be larger than, say, 2 to the 32 at most. So the memory complexity is not really high. So now let's go to the specific message expansion of SHA-1. This is message block, MI, or in our case it's M1. And this immediately defines the first 16 words of the expanded message, so W0 to W16. And then the expansion to the remaining words up to word 79 is done via this recursive formula. The important thing at this formula is that this is every message word here is a linear combination, linear over GF2, of the other message words. So what we receive here, if we consider all expanded message words, they form a vector space of dimension 512, meaning explicitly that we can add two expanded message words and we get a new valid expanded message word. This is what we call the linear message expansion. And so how do we use it for meet-in-the-middle attack? It makes it easy to find an expanded message which is 0 in the first 15 words and only contains something non-zero here in word 15 and then, of course, in the remaining part. But we can also find message words which are 0 in the last 15 words and only contain something non-zero in the first part. And now we think of these kind of message word as differences that we add to some base message that we want to test. So we take a base message W and we just modify it using these two difference patterns. When we apply the difference patterns V to W, then we will not change the backward computation here, this computation here. And when we change W with the U difference, we will not change this computation. And what we now do is just choosing one base message, then applying several of these V difference patterns. And there are exactly 2 to the 32 different such patterns, because essentially what we do is we fix this to 0, and then this is one word of 32 bits. We can choose every difference here, and then the rest is completely determined. And this allows us then to compute 2 to the 64 trials at the cost of only 2 to the 32 compression function computations, exactly in the same way we did before, where we could freely choose the left and the right part. So the problem with this technique is just we are limited to 30 steps. Yes?
It's a crucial step, so do you have any questions about it?
Thank you for this.
Can you explain again what you did with that? So XOR and there's difference in that one? So how do you determine if you're checking to see if there's collision between these?
I choose this base message, and then I modify it by XORing this difference V, and this gives me a bunch of messages which are all the same in this part, but they only vary in this part. And for all of them, I compute this until the middle, and I make the list here. And I do the same thing from this part, but just with the difference pattern U. So the messages I get in this part, they are all the same in this part, and they only vary here. And I make all these computations, and then I look if in the two lists I get here, I have a match. If I have a match, then this means, so assume we have a match in this computation and from this computation. Then this means that I can come from the IV with this message here, and then doing the computation here with this message, and I end up in this value that I want. That means that I have a preimage found when I use the message W plus V plus U. Because I can combine these two difference patterns, because the U will not modify this part here, and the V will not modify this part here. So they combine nicely. And this works for every value in the list. Yeah. This is what we do. Yes?
So there's left and the right-hand side, where you actually look for zeros and the zeros, asymmetric fashion. Now you try to find a match in the middle. Do you think you can take each part, left part and the right part, and further divide them in half, or like a one length? Do you think that would work, or would it be
So making four parts, and then which gives you more
4,
passes.
8,
But
16, so on and so forth.
the problem is that we really need, with the modifications we do here with the U part, we really need that in the other modifications. So with the V part, that we modify this part, this has no differences here in this part. And this is not possible if you split it more.
Another thing, for this kind of procedure, you have several starting points. So for us, the data that we have is this IV and the preimage that we are given minus IV. So we have to start from them, and we have nothing more to start from. So we take computations, and we meet somewhere. As soon as we meet somewhere, there is no more freedom left. And we cannot repeat our process anywhere else.
Okay.
Unless we are able to come up with some smart computations in the middle and try to mesh it, but it's the way around difficult.
Because this is the optimal choice to pick that right in the middle, not somewhere else.
Yes. So as long as you are given fixed input and fixed output, probably the best strategy for you is to start from them and with some.
From complexity point of view, yeah. All right. Thanks.
So the problem with this is that it only works for 30 steps. Because we are limited, we cannot have more consecutive steps with 0 differences, because the vector space of our messages, as I mentioned, 512, which is 16 32-bit words. This is determined by the message, by the way the message is expanded. So we have to find some way how we can extend this to more steps. And now, just the most straightforward way is to compute all the missing steps in between. So we do the same principle. We take U difference that does not modify the first 15 steps. We take the V difference, which does not modify the last 15 steps. We compute from both sides with every possibility we have, but we end up like this. So we have a list here, and we have a list here, and we have a number of steps that is just left in the middle. And we have to connect them. And the straightforward way is just to compute. So if we get a state here, we compute every possibility. So here we compute the possibility W plus V plus U. And from here, we compute the possibility W plus U, nothing, and so on. But this means that we lose somewhat the meet in the middle idea. Because these computations in the middle, we have to do it for every combination that we do. But for most of the messages that we test, we don't have to repeat these steps, and we don't have to repeat these steps. And this gives us a speed-up factor of this, if n is a total number of rounds. And this is what we call an accelerated search, because we still test every message. So we have to do some substantial computations for every message that we test, but we can save, for most messages, a number of rounds that we don't have to recompute. This is the idea. And of course, this works for any number of rounds. We can just expand this middle part. And what we get out of this is the following curve. What we see here is the number of steps of SHA-1, and what you see here is logarithmic complexity with this accelerated search. So, and here, these are the two results from Crypto 09 and Crypto 08. This is the Deganier-Rechberger result for 44 steps. It is faster than this accelerated search. And this is the result from Crypto 09 from Aoki and Sasaki, which worked for 48 steps. And you see that this is already slower than this accelerated search that we propose. And in fact, it has exactly the same complexity as when you do it with accelerated search for the full number of rounds. So what we propose is, as I said, maybe not consider this as a real shortcut attack, but at least what you should do is, when you design a future attack, it should be faster than this accelerated search. So at least what we do now in the second part of the paper, we want to try to have faster attacks than this accelerated search, and we can do it for reduced number of rounds. And we will do it with a technique that we call probabilistic partial matching. Partial matching is a known technique, and we just extended it to this probabilistic variant. And what we do here is, when we look at the picture, we have this U difference that does not introduce differences in the first 15 steps. And now what we do is just we ignore some number of differences that are introduced during the computation. So we just do like if the U would not introduce differences until step 20. But it does. It introduces two differences here. And we do the same thing in the backward direction with the V pattern. We just ignore the gray differences here. But otherwise, we do the same thing as we did for the 30 steps initial basic attack. So we compute for all possibilities of V until here, and we compute backwards for all possibilities of U until here. But now, when we have a match here, it's not sure that we really found a preimage. And if there is some message combination would be a preimage, it's not sure that we detect it here, because maybe we were somewhat wrong, but we know that we are somewhat wrong with this computation. But we can choose a subset of bits for this checking part here, which is not affected or only very not significantly affected by these differences here. So we have this probabilistic behavior here. In particular, this introduces some probability that we do not detect an actual preimage. So we lose some preimages in our testing process, and this increases the complexity of our attacks. So we must test more preimages. But as an advantage, we can attack much more steps, and when we compute this number of preimages that we have to test more and so on, we end up with attacks that are faster than accelerated search up to 56 steps, like this. And you remember best before was for 84, for 48. So these triangles here are what we can do with this probabilistic partial matching. We are faster than accelerated search until 56 steps. So, as a summary, the improvements we could do, so both ideas, accelerated search and probabilistic partial matching, we found it by this way of looking at the meet-in-the-middle attack with linear message expansion. That was not done before. Meet-in-the-middle was applied to linear message schedule, but this way of combining these differences, that was not used before. And this allowed us, so this makes our extensions quite not obvious, but straightforward somehow. So we showed that meet-in-the-middle attack combines nicely with this linear message expansion. Then we proposed this accelerated search that should be taken as a bar for better attacks, and not the generic complexity of 2 to the n. And we could, by our own, present better attacks for up to 56 steps with this new technique, probabilistic partial matching. Thank you for your attention.
So, other than the obvious answer, why SHA-1? Why not new ones? Because there are a lot of specific things that you use in SHA-1. Most things that are too general. Most techniques they use are pretty general, or seem to be too general. Is that intentional?
We heavily use the linear message expansion.
I understand that, yeah.
We basically described it in a way that it's
Yes.
familiar. Although we also have something which is more SHA-1 dedicated that not easily applied to other
Oh,
things.
I see. You do have it.
So, well, for example, we have also looked at SHA-2, which is also a natural object, but
Well, actually, I was going to say something earlier. The SHA-3 canvas where they process left and right fashion. Some of the hash functions do that. And if you look at the
There's two things.
candidates.
Two things which are really different and which make it difficult to apply this to the SHA-3 candidates is not a linear message expansion. So this is really really specific to linear message
Right.
expansion. But this applies to essentially every hash function that has linear message expansion. There are some others. But what makes it difficult to apply the meet-in-the-middle technique in general is when the inner state of the hash function is bigger than the output. And this is typically the case for all SHA-3 candidates. So then you cannot do anything with meet-in-the-middle. Because for meet-in-the-middle, yes, you match on this inner state, and when this one is larger than your output, then you just lose too much.
Yeah, so if I remember correctly, so this attack on the full SHA-1 is faster, so the complexity was faster than exhaustive search.
Yes.
But is the complexity the time complexity only? Because some people always do the time complexity times the storage complexity.
No, this is only time.
And if you combine them, is it still faster? Because I don't remember what the storage complexity was.
You have to store one list of 2 to the 32 states.
So if you combine them, then it would be...
there are some memoryless optimizations of meet-in-the-middle search which you could apply. We just didn't set this target, but if you want it to be memoryless, it can be memory safe.
Margin is smaller.
Yeah, the thing is, when your memory complexity is reasonable even now, like on like to the 20 about it, that having this metric of multiplying time in memory doesn't make much sense because the memory access is very fast.
Yeah, for these small values.
For these
yes.
small
Yeah,
values.
yeah.
And you can do it just with less memory, without losing anything. So you can maybe use 2 to the 5 states or something. And you get the same complexity without any trick.
Okay, nice.
Christian, do you have questions?
No, I enjoyed the presentation very much. Thank you.
Okay. Thank you so much, Simon.